Okay, we're looking at the logarithms review, and we're going to look at some logarithm graphs. So if we look at log base 2x, we're going to remember we can put this in as log base 2x. If we don't have the log base button, we can remember that we can always type it in like this. Remember, put the log on the bottom. So we're going to get log x divided by log 2. Or if we use the log base button, we can go math, and then we can arrow down or arrow up to A, pick that, and then we can go to, come on, 2, join us. Oh, a whole bunch of 2's. So we can go math, down to A, or up to A, enter, base 2, x. And we can press graph, and you'll see that the blue and the red, woo, we need to change our window. Zoom, the blue and the red are the same. What's to be noted about these is that if I put the other one in, which on your paper is a half, so instead of having a 2 here, I have a half as my base, you end up with a reflection in the x-axis, which would also be the same as if I, instead of putting a half down there, if I put math log base 2x, if I put a negative in front of it, instead of putting a half down there, negative math 2x, we would do the same thing as the other way because that's just a reflection in the x-axis, and that's what that fraction does, is it causes a reflection in the x-axis. Okay? So what we also need to note here is that we actually have a vertical asymptote for every log function at y equals, oh my goodness, x equals 0 on the y-axis. The only thing that can move that asymptote is if we have a horizontal translation to the right or a horizontal translation to the left. So your horizontal translation on a log function actually gives you your asymptote. What does that mean? If we have y equals 3 log 2x minus 3 plus 7, I actually have a vertical asymptote at x equals 3. Why? Because it's the only thing that moves it, and my log graph is normally situated at x equals 0. Okay. That's what those graphs look like. You can graph them onto this graph. Going through transformations. So we're comparing this y equals to log base 3 of x, because we can only compare if they have the same base, because that base 3 doesn't change anything in this instance. We have to compare them with the same base. What we need to remember is to take this 2 out. So before we state any transformations here, we have to remember to take out that horizontal stretch. So we're going to get negative log base 3 2x plus 3 minus 3. And now we can actually state them. So we have no vertical stretch, sorry. We have a horizontal stretch. A vertical stretch would be in front of the log here, and we have a 1, so we don't have a vertical stretch. So we have a horizontal stretch by a factor of, and remember, you would never write BAFO. You would write horizontal stretch by a factor of. You'd write the whole thing out because we can't assume that people know our short form. 1/2, because it always flips, about the y-axis. We have a negative in front of the log, so we have a reflection in the x-axis. We have a vertical translation 3 down. and we have a horizontal translation 3 right. And this horizontal translation is what gives us our asymptote, because our asymptote's normally at x equals 0. If our asymptote's normally at x equals 0 and we move it 3 to the right, our vertical asymptote now is going to be at x equals 3, positive 3. The domain is based on reflections or not. So your normal log function looks like this. So its domain is usually x is greater than 0. Or, yeah, greater than 0. However, if your asymptote moves to the right or to the left, it's going to be greater than or equal to whatever the heck that asymptote is. What's going to cause it to be less than, though? If I have a reflection in the y-axis here, so anytime you get a reflection in the y-axis, your domain is going to change to x is less than the vertical asymptote, because the entire graph will flip to the left. So the domain of this graph is x such that x, is it going to be greater or less? Well, we have to check. Is there a reflection in the y-axis? If there's a reflection in the y-axis, there'd be a reflection in front of this 2, a negative in front of this 2. Is there? No. So there's not a reflection in the y-axis. So it's going to be greater than. It's not going to be less. It's going to be greater than my vertical asymptote, which is negative 3. Oh, we didn't go 3 right. We went 3 left. Silly me. Probably been freaking out this whole time. It's 3 left, because this is a plus 3. So then this is going to be minus 3. And this is going to be minus 3, actually, because we moved 3 to the left. XER. My range is YER, because it keeps going on forever. My y-intercept in this case, y-intercept is x equals 0. So you're going to get y equals negative log 3, 2 times 0 plus 6 minus 3. And when you punch that into your calculator, you get y is approximately negative 4.63. That's going to be your y-intercept. Your x-intercept is a little harder to solve, and you have to use your exponential deal. But your x-intercept is when y equals 0. So our equation is going to be 0 equals negative log base 3, 2x plus 6. And you need to solve for x. Okay? 2x plus 6 minus 3. You need to solve for x, but the only way I can change to solve for x, when I don't know what's in the base of a log or beside a log, I change to exponential, but I can't change to exponential in this form. So I'm going to have to first add the 3 over. Then I have 3 equals negative log 3 to the 2x plus 6. In order to change from log to exponential, I just have to have a log by itself with a positive 1 in front. So I'm going to still have to divide by negative 1 here first. And I'm going to get negative 3 equals log base 3 of 2x plus 6. And now I can actually convert to exponential because it's in the right form. So I'm going to get 3 to the negative 3, because the base of my log becomes the base of my exponent. What's with it doesn't stay with it, so the 2x plus 6 is what it equals. And it's to the exponent of negative 3. And then I just solve my math like I normally would. I'd get 3 to the negative 3 minus 6 equals 2x. And then take that answer and divide by 2. So x equals approximately, that's these little squiggles mean, 2 little squiggles, approximately negative 2.98. Let's look at the other one. So this one here, we're going to have to compare to y equals log 1/2 x. So let's take that negative 3 out. So we're going to get y equals 2 log 1/2. Take a negative 1/3 out. When you divide by negative 1/3, it's like negative 1/3. It's like multiplying by negative 3. So you're going to get negative 2 multiplied by negative 3 You're dividing by a negative a third. It's going to be plus 6. So what are my transformations? Well, I have a vertical stretch by a factor of 2 about the x-axis. So it's about the other axis. That half does nothing. It's the same base. I have a horizontal stretch by a factor of 3. Remember, your stretches are never negative. The negative causes the reflection about the y-axis. I have a reflection in the y-axis. What does a reflection in the y-axis do? It changes your domain. Remember that? Reflection in the y-axis causes your graph to, instead of being going this way, it's now going to go to the left. So your range is going to be less than. Your domain is going to be less than. I have horizontal translation 6 left, because it's always the opposite. So if I have a horizontal translation 6 left, I have a vertical asymptote at x equals negative 6, because my asymptote was at 0. It's now going to be moved off the y-axis 6 to the left, so now it's going to be at x equals negative 6. My domain, because of that reflection in the x-axis, is going to cause me to have an asymptote at x equals negative 6, and the entire graph will be not that direction. It'll be like this. So we're going to have x such that x is less than negative 6, xer, and my range is still yer. So less than negative 6 is from negative infinity to negative 6. It's not equal to, because the asymptote is on that negative 6, so it can't be equal to. And then this is negative infinity to infinity. The x and y intercepts, you do the same as the other one. Okay, the next thing we're going to go through is solving. All of these are going to say solve. We just have to figure out, the hardest part is to figure out what method we need to use. So we always check when it's exponential. It doesn't matter what type of exponential solving we have. Exponential means we have a base, and in our exponent we have variables. We're always going to try and check for common base first. And common base will work in this one. So I'm going to make them all be base 5. 125 is 5 to the 3. And then remember, we have to remember to distribute that 3 into the 2x plus 1. We also have to remember that 5 is 5 to the 1, and that 1 is very important because we're going to have to add it on. And then we're going to have 5 squared is 25 to the 3x plus 1. Okay, we're going to distribute. We're going to get 5 to the 6x plus 3. That's a 6, doesn't look like it. Equals 5 to the 1 times 5 to the 6x plus 2. Now these are the same base. When you have two bases and two exponents, remember you add the exponents. So we're going to get 5 to the 6x plus 3 equals 5 to the 6x plus 3. So we actually have the exact same graph. So they would have infinitely many. Now, does this rarely happen? I would say it probably doesn't. But I'm just proving a fact that these two graphs look very different, but they're actually the same. Okay. We're going to look at number 2. So number 2, we look and say, can we do common base? As of right now, we can't. However, you also have to look and see. This is 3 to the exponent 1, and this is 24 to the exponent 1. If you have two bases that are to the exponent 1, you can put them together. So we're going to divide by 3. And we're going to get 4 to the 2x plus 1 equals 8. And now we can actually make them common base. I'm going to do two methods. I'm going to do common base. And then because there's only one exponent, I can also change it to a log. So I'm going to do both. Your choice. So common base. 4 is 2 squared to the 2x plus 1. And 8 is 2 cubed. Here we're going to get 2 to the 4x plus 2 equals 2 to the 3. Now that we have the same base, we're saying that this is base 2, this is base 2, so this exponent must equal this exponent then. So we get 4x plus 2 equals 3. Subtract 2. 4x equals 1. Divide by 4. X equals a quarter. Remember, we could also, if this wasn't algebraically, we could y1, y2 this, and hopefully we get a point of intersection when x equals a quarter, or 0.25. We're going to check it through a log. So, convert to log. The moment you have an exponential with only one exponent and two bases, we can convert it to a log. So we're going to go log. The base of my exponent, which is 4, is going to become the base of my log. What's with it is going to not stay with it, so we're going to get 8 beside it, and it always equals your exponent. So then we're going to subtract 1 from both sides. And we can't subtract that from the 8. These are connected. So you can't go like log base 4 of 7, which some people try and do. So we're going to do log 8 divided by log 4, or log base 4 of 8, which is 3 over 2, or 1.5. So we're going to get this here is 1.5. And then we're going to subtract 1 from it, equals 2x. So we're going to get 0.5 equals 2x. When you divide a half by 2, you get x equals a quarter. And they match. So it's whichever method you seem to like, you can do. So remember what I said for method 3 here, we have solve again. But this time it has a log. It's not bases, it's not exponential, nothing like that. What I told you is if you don't know the base, so say the variables here were the 6's, or the variables beside the log, what I told you to do every single time is you need to convert to exponential. Now, could we not y1, y2 this? Absolutely. And see where they intersect and give me the x value. However, we're going to do them all algebraically because that's better. So, the only way I can convert to a log is if I have a log by itself with a 1 in front. Right now I have this 2 in front. So I'm going to convert to exponential from a log. So I can't convert a log unless it's in the proper form, which right now it isn't. I need to have a 1 in front. So I'm going to divide both sides by 2. So now I have log base 6 of x plus 2 equals 2. And then I can convert to exponential. So I'm going to get 6 squared equals x plus 2. The base of my log becomes the base of my exponent. What's with it doesn't stay with it. What it's equal to becomes the exponent. So now I have 36 equals x plus 2. Subtract 2. And I get x equals 34. And I can check it with my calculator. All right. Next question. Okay. Once again, I'm back to exponential. I can't divide that 4 over. Yes, it's to the exponent 1. However, I can't divide it over because the 9 has an exponent, so I can't make it join it. So I can't do common base. I can't convert it to a log because there's 2 exponents. You can only convert to a log if there's 1 exponent. So the only option I have left is logging both sides. And when I told you to do this, I always told you to log base 10. So log base 10 of 4 times 7 to the x plus 2. Remember you have that extra step in here if you have that 4 in front? Log base 10, 9 to the 2x minus 3. The only reason why I tell you to write base 10 is to try and get people to stop making the 4 and the 9 as your bases. So this one I can split by addition. That's that extra step you have to do when you have that 4 in front. So log base 10 of 4 plus log base 10 of 7 to the x plus 2 equals log base 10 of 9 to the 2x minus 3. So I'm going to take these exponents and I'm going to drop them in front. So I'm going to get log base 10 of 4 plus x plus 2 in brackets. And I put in brackets so I remember to distribute it. Log base 10 of 7 equals 2x minus 3. I drop that in front. In brackets, log base 10 of 9. And now I have to remember to distribute. So I'm going to get log base 10 of 4 plus x log base 10 of 7 plus 2 log base 10 of 7 equals 2x log base 10 of 9 minus 3 log base 10 of 9. Our next step is to get all the x's on one side and everything else to the other. So I'm going to move this x log 7 to the right and the negative 3 log 10, 9 to the left. So I'm going to get log base 10 of 4 plus 2 log base 10 of 7. I'm going to add the 3 log base 10 of 9 to this side. And then on this side, I have 2x log base 10 of 9. And I'm going to subtract the x log base 10 of 7. The reason why I get my x's to one side is so I remember to take that x out. So this side's going to stay the same. Log base 10 of 4 plus 2 log base 10 of 7 plus 3 log base 10 of 9 equals x, and what's left over is 2 log base 10 of 9 minus log base 10 of 7. And then I'm going to divide that over. 2 log base 10 of 9 minus log base 10 of 7 over 2 log base 10 of 9 minus log base 10 of 7. Now you could put these into your calculator and get a decimal, but if they say exact value, there is actually an extra step. So on the top, I can put all those logs together, but I'm going to drop the log base 10 for now. So I'm going to get x equals log base, or just log 4 plus log 7, and I'm going to bring the 2 up, squared, plus log 9, and I'm going to bring the 3 up, cubed, over, on the bottom, I'm going to put log 9 squared minus log 7. Now, if you notice, they're all base 10. So I can put the entire top together by multiplication because they all have plus 1s together in front of them. And I can put the bottom together by division. So I'm going to get log 4 times 7 squared times 9 cubed, which is going to be a large number, over log 9 squared divided by 7. So I'm going to get x equals 4 times 49 times 9 cubed. I'm going to get log 142,884 over log 81 over 7. Now remember, I could write log base 2 of 6. I could write it like this, log 6 divided by log 2, correct? So if I have log 14,000 or 142,884 divided by that log, I can actually rewrite it as log base 81 over 7, 142,884. That's if they want exact values. If they want decimals, you can punch this right into your calculator and you're golden. Okay? So if you can't make common base and you have two exponents, you have to log both sides. That's what you have to do. I'm going to erase this so no one gets confused with it being there. Okay. This method, you have log base 2 of 3x plus 1 equals 2 minus log base 2 of x minus 1. You have two log base 2s. So that's a hint. You need to move them to one side and number on the other. Get logs on one side. Okay? So we're going to have log base 2 of 3x plus 1 plus log base 2 of x minus 1, and it equals 2. Now I know in order for this one to work, x is going to have to be greater than negative a third. And in order for this log to work, x is going to have to be greater than 1. Because if it's any numbers less than those, you're going to get negative beside the log and it's going to be extraneous. Well, which one of these restrictions encompasses both? This is negative a third, the red. This is greater than 1. The only place where there's two colors is here. X is greater than 1. So as long as your solution is greater than 1, any of your solutions, they're not going to be extraneous. Okay, so they have the same base. We're going to put them together. So we have log base 2. They have plus 1s in front, so we can put them together. They have the same base, so we can put them together. There's a plus 1 in front, we multiply. So we're going to get 3x plus 1, x minus 1 equals 2. We're going to get log base 2 of 3x squared plus x minus 3x minus 1 equals 2. So we get log base 2 of 3x squared, put these together, minus 2x minus 1 equals 2. And now we're stuck. That's where most people get stuck. Remember, if you don't know what's in the base of the log or you have the variable beside the log, you convert to exponential. So at this point, we're going to convert to exponential because we don't know what's beside the log. So we're going to get base of the log because base my exponent, what's with it doesn't stay with it. So 2, and it's going to equal 3x squared minus 2x minus 1. And now we're back to grade 11. So we get 4 equals 3x squared minus 2x minus 1. And when you have a quadratic, you always have to get everything to one side set equal to 0. So we're going to get 0 equals 3x squared minus 2x minus 5, which is decomposition. What multiplies to give me negative 15 and adds to give me negative 2. It's going to be positive 3x minus 5x. Group. Plus sign in between. You can take out a 3x, and I'm left with x plus 1. Take out a negative 5, and I'm left with x plus 1. So I actually left with 0 equals x plus 1 and 3x minus 5. And then I have to solve them. X plus 1 equals 0. X equals negative 1. 3x minus 5 equals 0. 3x equals 5. X equals 5 over 3. This is the only one that's greater than 1. This one doesn't work. So it's extraneous. So sometimes you're just asked to find the extraneous root, and no matter how much you y1, y2, it's not going to show you the answer that doesn't exist. So if you take that negative 1 and you plug it back into here, into the original, because that's where you always plug it, 3 times negative 1 is negative, 3 plus 1 is negative 2, and you can't have a negative beside a log. The next one is different than the last one. The last one had 2 logs and a number. This one has 3 logs. When you have 3 logs, just get all the logs on one side together and all the logs on the other side together. Combine logs. And we can because they all have 1s in front or negative 1s in front, and they're all base 5. So I'm going to put the logs on the left together. So I'm going to get log base 5, x minus 18 is on the top because there's a plus 1 in front, and x is in the bottom because there's a negative 1 in front of the log. And then here I have log base 5 of 7. From here it's easy. If this is log base 5 of this equals log base 5 of this, then it only makes sense that the two reds are equal. So we're going to have x minus 18 over x equals 7. Solve. Multiply by x. X minus 18 equals 7x. Subtract x. Negative 18 equals 6x. Divide by 6. X equals negative 3. Check it, always for extraneous roots. If I fill the negative 3 in for x here, negative 3 minus 18, it doesn't work. As such, this doesn't work. Because when you fill it in, it doesn't work. You have no solution. So the two are not going to cross. Is that always the case you have no solution? No, just sometimes.